So our basic question gives us a probability sample of 1,785 adults, and the poll is whether they attended church or synagogue during the past week. We suppose that 40% of the adult population did attend, and we want to know the probability that this probability sample would come out within plus or minus 3 percentage points of this true value. So part A asks us for the mean of the sampling distribution of p hat and what our standard deviation would be. Alright, so our mean is equal to our population proportion, or p. So we would take our 40% and convert that to a decimal, and our mean is 0.4. And our standard deviation, here's our formula. We have the successes and then 1 minus p, and or q, which would be our failures. So p and times our failures divided by our sample size. When we plug in the numbers they give us into that formula, we have 0.4, our successes, times our 0.6, which is 1 minus p, divided by our n, or our sample size, of 1,785. And then that gives us a standard deviation of 0.0116. Part B asks us to explain why we can use the formula for the standard deviation of p hat in this setting. So we're basically asked to explain why we can use rule of thumb 1 here. So rule of thumb 1 states that our formula for the standard deviation of p hat is used when the population size is at least 10 times as large as the sample size. The population of the U.S. adults is obviously much larger than this sample that we're given of 1,785. And going on to part C, my nails are gross. Going on to part C, we're supposed to check that you can use the normal approximation for the distribution of p hat based off of what rule of thumb 2 states. So rule of thumb 2 states that normal approximation for p hat distribution can be used only when np is greater than or equal to 10 and nq is greater than or equal to 10. So, plugging in the information we figured out before, this is our n and this is our p, our 40%, that equals 714, and n and q multiplied is also greater than 10. And this is our 1 minus our p again. So for the last part of the basic question, part D, we're asked to find the probability that p hat takes a value between 0.37 and 0.43, and we're asked if an SRS of size 1,785, given a result p, will be within plus or minus 3 percentage points of the true population proportion. Essentially what we're being asked is to find the probability between 0.37 and 0.43. So to find the probability that we'll get a value between those two numbers. So we're going to use our z-score formula and plug in those values. And then we're going to take our standard deviation that we found in part A, right here, our 0.0116, plug that in as well. From that we get the probability of negative 2.586 is less than z, which is less than 2.586. And we go to table A from there, and we find the z-scores for these individual values. So after going to table A, we have negative 2.586. This z-score would be p equals 0.0049, and then this one would equal 0.9951. After subtracting those values from each other, our difference is 0.9902, and we can conclude that approximately 99% of the samples will give p hat within plus or minus 3% of the true population proportion. Okay, so in this advanced question, researchers are comparing two methods for estimating tire wear. One method uses the amount of weight lost by a tire, whereas the other one uses the amount of wear in the grooves of the tire. So there's 16 tires, that's our sample, and both methods were used to estimate the total distance traveled by each tire. In Part A, we are asked to construct and interpret a 95% confidence interval for the mean difference mu and the estimates from these two methods of the population of tires. And Part B asks us if our interval in Part A gives a convincing evidence of a difference in the two methods of estimating tire wear and to justify our answer. Alright, so for Part A, we need to go to the calculator and we go to Stat, Edit, and we put in all the data that we have from our chart in the differences columns. We put that in, and then we hit Stat, Calc, and then one var stats, and that gives us this information that we need for our one sample t-test. It gives us our S, our standard deviation, and our mean. It gives us a mean of 4.556 and a standard deviation of 3.226. So now we're going to plug that in to our t-test. And from our t-test, this is our confidence interval formula. And then we plug in our S, our standard deviation, into there, and our sample of 16 tires in the N, and also our, I said that already. So, and then to find our T star, our T, we are going to go to table C and find the degrees of freedom. So we do 16 minus 1 equals 15, and we go to 95% because they're asking for a 95% confidence interval. So we go to that in our table C in the textbook, and that gives us 2.131 degrees of freedom. And then we plug it in. We plug all this into our confidence interval here. So we have 4.556 plus or minus 2.131 came from that. And then our 3.226, which came from our standard deviation, and our N here, our sample here. And then we plus and minus for both of those, giving us 6.275 and 2.837. So from that, we can determine we are 95% confident that our 2.837 and 6.275 interval shows the true mean difference. So Part B of the advanced question asks us if our interval in Part A gives convincing evidence of a difference in the two methods of estimating tire wear. And we can say yes, that it does give convincing evidence because there is a positive range and the difference is not at 0. So it's falling between 2.837 and 6.725. And it's a positive range and it's not at 0. In the AP question, so manufacturers want to develop balls that will travel as close to a 291.2 yards without exceeding that distance. So a particular manufacturer has determined that the distances traveled for the balls it produces are normally distributed with a standard deviation of 2.8 yards. Part A asks us if the manufacturer sets the mean distance traveled to be equal to 288 yards, what is the probability that a ball that is randomly selected for testing will travel too far? Okay, so for Part A, we're taking the z-score formula again. We're taking 291.2, which is what it cannot exceed, but we want it to be the closest to, and our 288 that they gave us in Part A divided by our standard deviation of 2.8 yards. This gives us 1.14. So we'll go to Table A, find 1.14, and that gives us 0.8729. We're subtracting 1 minus 0.8729 because we want to find the probability of the ball going too far, which is to the right side of our distribution curve or whatever. And so this gives us 0.1271. and the probability of a ball traveling too far is about 12.71%. In part B, if we assume the mean distance traveled is 288 yards and that the 5 balls are independently tested, we are asked what is the probability that at least one of the 5 balls will exceed the maximum distance of 291.2 yards. Okay, so this is how we would write out our probability, and we're taking 1 minus p, or the probability of the 5 different distances is less than or equal to 291.2. We're going to plug in the information we found in part A, our 0.8729 found from table A, and we're doing 1 minus that to the 5th because of our 5 different distances, and so that ends up being that, and we take 1 minus 0.50678 to give us 0.4932, and that gives us a 49.32% chance that at least one ball will exceed the maximum 291.2 yards. Lastly, in part C of the AP question, we're asked if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of 291.2 yards, what is the largest mean that can be used in the manufacturing process? So this manufacturer wants to be 99% confident, so we're going to find 99% in table A and find a z-score of 2.33. Next, we plug this into our z-score formula. So 2.33 is equal to our 291.2 maximum amount of yards to be traveled, minus our mean, which is what we're trying to find, divided by our 2.8, or our standard deviation. And then we're going to do algebra to solve for our mean there. So do 2.8, cross that out, blah, blah, blah. And then we multiply these two and add this to the other side and subtract this from that to give us 291.2 minus 6.524 equals our mean of 284.68. So that means that if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed our maximum distance of 291.2 yards, the largest mean that can be used is 284.68 yards, or about 285 yards.